So let's define another really important example of an equivalence relation. So consider G a group and H, which is a subgroup of G. So H is a subgroup. And then consider the following equivalence relation. A is equivalent to B if, let's see. A is going to be equivalent to B if B equals A times H for some H in H. And so A and B are going to be elements of G. Okay, so why is this an equivalence relation? Well, let's verify the three properties of equivalence relations. So first, reflexive. So I need to show that A is equivalent to A for any A. And of course, so 1 is in H, so A equals A times 1. That's good. That's not so bad. Now we need to check symmetry. So symmetric. So let's say B equals AH. Oops, that's B. B equals AH. So now that B equals AH, well, I can say, oh, whoops, this H should be a big H, right? Because I'm talking about the whole subgroup here. So, but back to symmetry. Symmetry. So I can multiply on both sides by H inverse, right? H inverse, H inverse, and then what I'll get is B H inverse equals A. And because H is a subgroup, H inverse is an H. So we definitely use that H is a subgroup. So that means that, B is equivalent to A. So that's check. And finally, transitivity. So here we use the identity axiom of the subgroup. Here we use the inverse axiom of the subgroup. Now we're going to use the closure axiom of the subgroup. So here's how it'll work. We have A equivalent to B and B equivalent to C, and we need to show that A is equivalent to C. So how can we do that? Well, we expand the definition. So we'll say B equals AH, and then over here, this turns into C equals B times, well, it's not the same element necessarily as this guy, so it could be H prime, so for some H prime in H, right, for some H prime in H. Now, what can we do with this? Well, we have a formula for B, so let's plug it in right here. So C equals, so this implies C equals H prime, and now the closure axiom, H prime is in H. So then, so C equals A times H prime, that's a check. So this is an equivalence relation, and so again, by the equivalence of equivalence relations and partitions, so we get a partition. So we get a partition, and so what are going to be the sets in those partitions? Well, it's going to be the sets where, well, it'll be the sets, so, right, remember for partitions, the partition sets are something like the set of, B such that A is equivalent to B, or something like this. Right, so the sets for the partitions are going to be, it'll be, so that'll be, in this case, the set of all elements B in G such that B equals A times H for some H in H. And we can write this in a little bit easier way. We can just write AH such that H is in H. And so the mathematical name for a set that looks like this, which I guess I'll define right now, the coset of A, which is denoted AH, because we're kind of thinking like we're multiplying A times everything in the subgroup, is the set AH for H in H. And what we've shown is corollary of the theorem about equivalence relations and partitions is that the cosets partition G. I'll say the cosets AH partition